In this video, we will talk about sampling from distributions and making histograms. So first of all, let us recall the random real command and the random integer. So if we want to sample from a discrete distribution, we can use the random integer command. And that will give us a random integer between 0 and 1 by default. So this is essentially like a coin toss. So we can use this structure. So say 0 and 1 and toss a coin 20 times. And this will give us 1 or 0 or head or tails. We can also throw a dice in the same way. So we can request a random integer between 1 and 6. And this will throw a dice 20 times. So these are examples of sampling a discrete distribution. We can also sample from a continuous distribution using random real. So if I just type random real, it will give me a random real between 0 and 1. So that's the default interval. I can specify the interval explicitly here and then say I want 20 samples, and that will sample 20 times. So obviously this is a uniform distribution between 0 and 1. I could also ask for other intervals like 0 to 6, for example. That will sample uniformly between 0 and 6, or 2 to 7. And that's the uniform distribution I had asked for before. Now, let's suppose I want to sample from another distribution. Mathematica has a way to do that by default, and that's the random variate command. So we can ask for instructions here by putting a question mark. So we see that we have to specify the distribution and how many samples we want. So let us recall from a previous video, we constructed the uniform distribution. So uniform distribution. Let's suppose I want to sample this distribution from 2 to 7. I can specify 2 and 7 here. Let us recall the structure of this command. So we specify the minimum and the maximum. Okay, so I can say uniform distribution between 2 and 7. If I ask for the PDF, let us recall that the PDF is of this form. And how do I sample this distribution? So obviously we can use random real, but let's use the random variate command. So I would say random variate and then uniform distribution. And that will give me 1 number. And if I want more numbers following these instructions, let's say I want 20 numbers. And I specify that here. And so I get 20 numbers from this distribution. And obviously this result and this result are equivalent. Now, of course, this random variate command is more powerful because I can use any distribution I want here. So let's consider another distribution. For example, let's consider the exponential distribution. So you can look at the documentation and see that this depends on one parameter, lambda, a scale parameter. You can read more about it here. And let's write down the PDF for that distribution. So PDF exponential distribution, and we have to specify a parameter, lambda, and let's write it in terms of a variable x. Okay, so this is the probability density function of the exponential distribution, and if I want to sample from that distribution, I can use random variate and then exponential distribution, and then I have to specify the parameter here. Let's suppose that the parameter is 0.5, and let's suppose I want 20 samples, and so I got 20 samples that are distributed not uniformly now, but they're distributed according to this exponential distribution. We will see in a little bit, we will plot this result. Actually, we can plot it now. Let's do a list plot of this result. So it looks a bit like this. Of course, it doesn't look exponential because the number of samples is small. So let's try a bigger sample here. Let's try 1500. Okay, and it looks a bit strange. And the reason it doesn't look, of course, like a exponential distribution because I haven't binned the results. We will see in a little bit how to do that, how to do a histogram and bin the results. So let's postpone this discussion for a bit. Let's consider another distribution, or actually let's consider another way to sample from this distribution. So that's called the inverse function method. So let's see. So the inverse function method is described here in these notes. Let's assume that we have a programming language where we can sample from the uniform distribution, but not from other distributions. So we cannot use Mathematica's ability to sample from the exponential distribution, or let's suppose we want to have some strange distribution that Mathematica doesn't have in its database, and I want to sample from it. How can I do it? Well, obviously we cannot do that because if that distribution is not in Mathematica's database. So what we could do is we could use the inverse function method. So if this is a continuous distribution, we can define the CDF, or the cumulative distribution function, which is defined as this integral from -infinity to x of the PDF, or the probability distribution function. And let's set that equal to some random variable y. And if you invert that PDF and solve it in terms of x, then x is the inverse function f of y. And we know that this function always exists, and it's monotonic, a monotonically increasing function. So that's for the example we discussed in the previous video for the Gaussian distribution. That's the Gaussian, and that's the CDF. And the algorithm for generating a random variable with PDF given by f of x consists of these steps. So first we calculate the CDF, then we invert it and solve for the inverse function in terms of x. Then we sample uniformly a variable u from 0 to 1. And we know that the CDF goes from 0 to 1. So basically we sample uniformly this variable u, and then we return the sample, which is f minus 1 of u. So here's an example. Let's consider the exponential distribution I just discussed. we can calculate the CDF either by integrating the PDF, or we can ask for it directly. So I can just say CDF exponential distribution, and here it is. And then if that's the CDF, then I want to invert that and solve for X. So to do that, I can say solve, and I can just copy and paste this. And let's suppose that this equals Y, and let's solve it for X. Okay, so I get this solution. It looks a bit strange, but I can massage it a bit into a slightly more useful form. So first of all, this is a constant. It happens to be a complex number here, but C is also complex, so I can set the result to some real constant if I want. And also I have a 1 over 1 minus y that can become log of 1 minus y with a minus sign in front of it. So I could write the solution as 1 over lambda and then log and then 1 minus y. And then because I inverted this, I get a minus sign here. And let's see, so the constant is fixed by specifying the limits of the integral. And you can look at the algebra here, and you can see that I can basically set this constant to 0. Okay, so now let's see. So this means I can sample uniformly this variable, and the result will be exponentially distributed, basically. So the instructions to do that are written here. So if I do random real, and let's call this U, and let's suppose this is randomly distributed between 0 and 1, and let's ask for 20 samples. And then I can simply calculate this quantity and put U here. So that's a uniformly distributed variable. Then the result will be distributed according to the exponential distribution. So let's call this X. And I need to specify what lambda is. So let's set lambda equal to 0.5. And let's try this. Okay, so here I have a sample from the uniform distribution between 0 and 1, and then I plug the results into this expression, and I get some numbers that are distributed between 0 and infinity, basically. So this is the exponential distribution. So this result, this algorithm is equivalent to this algorithm, this command, where I use the random variable command and I specify that I want to sample from the exponential distribution. And in a minute we will do histograms based on these samples. But before we go into that, let's just do a second example. Let's consider the Rayleigh distribution. So the Rayleigh distribution, if we look at the notes, it has this form. So let's repeat the previous steps. So let's ask for the PDF of the Rayleigh distribution. Let me just clear the variable lambda first. And let me clear the variable x and try again. Okay, so that's the Rayleigh distribution. This result here is equivalent to what we find in a textbook. But we have to be careful about the normalization and make sure that it's 1. Okay, so here the Rayleigh distribution has been defined with lambda equals 1, but in general it would have some scaling parameter lambda here. Okay, so to sample from that, we need the CDF if we want to use the inverse function method. So that's the CDF. So now I can say solve, let's call that y, and solve with respect to x. And here we get 2 solutions, and we can pick the positive one, and we can set this constant to 0. So let me set that to 0. Okay, so, and let's pick the positive one. And let's massage that a little bit. So again, the root of 2 can be brought into here, inside the root. And then the 1 minus y, the log, can simply change the sign of the log. And then we have 1 minus y as an argument. So this matches what we see in the textbook in notes here. Okay, so now we know that I can sample uniformly from this variable, and I will get a variable x that is Rayleigh distributed. So the algorithm for that would be, again, very similar to this. So let's do a random real 20 times. Let's pick lambda equals 1. And then x will be distributed like this. So let's try this. Okay, so now we get, again, a random real distributed between 0 and 1, and then another variable that's distributed according to the Rayleigh distribution. And of course, we could have done the same thing with the Mathematica command using random variate. But the purpose here is to find ways to do these operations that are independent of Mathematica, that do not use black box mathematical functions, so that you can also implement them in other languages if you want, like Python, MATLAB, C++, or Julia, and so on. So if we want to compare this to the default mathematical function, I can just say Rayleigh distribution here and use 1 as a variable, and then Mathematica would sample from that distribution and would give me 20 samples. And here I specified that lambda is 1, just like here. Okay, so now let's move on to describe histograms and how we can plot these results in a way that makes more sense. So how do we make a histogram? So if we consider a continuous sample space omega, as described in the notes, and a variable random variable x that follows a PDF f of x, then here's how to make a histogram. So first we make n measurements. That gives us n data points, as we've done here. And then to construct a histogram, we have to count the number of samples between x and x plus delta x. And we call that h of xi and xi plus delta x. So we have to do that for each bin I. And then, of course, the total number, if we sum over all these bins, we have to get n. So that's the total number of samples that we took. Now we can normalize this into a probability by dividing by n. And dividing h by n will give us the probability of x being between x and x plus delta x. As the number of samples increases, this should approach the probability density function. Okay, so here's a more concrete way to build such a histogram in Mathematica. So first we discretize the range into n slices of size delta x, so that delta x is b minus a divided by the number of samples. And then we have to count the number of samples in each bin. And this command will do that. And then, so here, if the data is stored in a vector y, these are my samples, then I count how many x values are between y and how many values y are between x and x plus dx. So this is what we do with this if statement. So if this is true, we increase the value of h by 1. So we're counting, basically, and storing the results into this vector h. And we can wrap this inside a do loop I, and repeat this for all members of the vector y. And then we return the vector h. So let's implement this. Okay, so let's suppose I want to take the results from the Rayleigh distribution or the exponential distribution. So let's take this result. So we have the exponential distribution here, and let's call this y. And let's do more samples. Let's take 1500 samples. And I don't want to look at them, so I'm going to put a semicolon here. Okay, so that's my variable y. And then let's suppose I want to use spacing dx that's equal to 1. And let's define the histogram bars. So let's suppose that these are given by, let's say, x. Let's take a range between 0 and 10 with spacing dx. Okay, so these will be the bars that are going to be used by the histogram, or the bins. So this procedure will count how many values, how many variables are between 0 and 1, how many are between 1 and 2, and so on. So to do that, we're going to wrap this command inside a do loop. So let's take this command and wrap inside a loop. So that we're going to say do, and then I has to go from 1 up to the length of the vector x. So we do that for all values of this xi. And we have to also loop over k. So over all the values of the vector y. So that would be a double do loop. But I can just say do one once here, and I can just type the second index with respect to which I want to loop over. So k will go from 1 up to the length of the vector y. And I close the curly bracket here, and I close the do loop. So let's do this. And I got an error. The reason is I haven't defined the vector h, of course. So I need to start to initiate the vector h. So let's use a constant array and let's zero it out. And here we have, it looks like we have 11 bins. So we construct a vector h that's going to be used for counting. So and we initiate the vector h to 0, and then we start increasing its value whenever we find a sample within a specific value, interval. Okay, so let's do that. And now let's look at the vector h, what it looks like. Okay, so now h looks like this. Now I could list plot that. And we see that that kind of looks like the exponential distribution. I can also say plot range all to look at it a bit better. So that does start to look like the exponential distribution. However, it's not normalized. So to normalize it, let's use this definition of the probability here. So we can use, let's say, P is the probability, and that's going to be H divided by the total number of samples. So let's say total H. Let's check, of course, the total of H is this. And the reason this doesn't match this is that I only looked at samples between 0 and 10, and some numbers have fallen outside that interval. So that's the reason. So we could look at higher values of x here. But anyway, so let me introduce a number n here. That's 1500. And put an n here. Okay, and then to make sure that this is actually a probability and it's normalized correctly, I'm going to divide by n. So because I ran this, h became 0 again, so let me run this again. And now p is normalized, so I can plot p here. And then that looks like exponential. Let me plot the PDF of the exponential distribution with lambda equals 0.5 with respect to x, and x going from 0 to 11, let's say. So this is what that looks like. And let's show both of them together. Okay, so this is what it looks like. We can try increasing the number of samples. So let's try 15,000. And let's try doing this loop again. And this. And this again. So this is what it looks like for now. Okay, so let's now we can do this procedure using bin counts. So I can say bin counts, and then I can supply the data y. So let's look at the structure of this command. So bin counts the number of elements xi whose values lie in successive integer bins. In addition, before we do that, let's also look at, instead of using list plot, I can say bar chart. So let's do a bar chart of P. Okay, and this now starts to look like a histogram, basically. Okay. Let's do a bin count. So this completed a bin count of that's equivalent to this double do loop that we discussed here. So I could define h to be this, and then I can normalize it. So I can say p equals h divided by n, and then I can say list plot p like before. And it looks like this. And of course I can also do a bar chart. Okay, so that's a histogram, but I could directly say histogram. So let's look at the command. So histogram, it can directly take the data as input and bin it, and then do a bar chart. So that's the structure of the command. So I can just simply supply the data here, histogram of the data y, and that will pick automatically a bin size and do a bar chart. Of course, you can specify the bin size yourself. So if I look at the histogram command, you can specify the bin width and so on. Okay, so with that in mind, let's look at the histogram of the data that we produced earlier. Just keep in mind that when you do a histogram, it's not normalized by default. If you want to normalize it, then let's look at the documentation. So over here, you can say histogram and put in the data there, and then say automatic, and then probability, for example. But if you are plotting a probability density function, then you can say automatic and then PDF. And then that will ensure that the normalization is such that you can compare this to a PDF. So I can say now plot. Let's plot the, let's repeat this plot of the exponential distribution here. And now we can show these two together. Okay, and now we see a bar chart or a histogram that's properly normalized because I used this command to make sure that this is normalized as a PDF, so that the total area here should be 1. And then I plot a PDF, and then I show these two together in the same plot. So you would expect that for large numbers, the histogram should start to look like the PDF or the probability density function. And I can change the order so that I make sure this line appears on top. And of course, you can put axis labels here and so on. So now that we know how to do histograms, let's go back into our earlier results and do histograms of these. So remember, we sampled from the exponential distribution here. Let's plot the results. So in this case, we use the inverse function method. Let's take 1500 samples. Let's suppress the output, and then we will ask for a histogram of that data and normalize it as a PDF. Okay, so we get something that looks like an exponential distribution. Let's ask for more samples. Now it looks a bit smoother. Of course, if you only take a small number of samples, it's not gonna look very uniform. It's not gonna look very much like the PDF. It only looks like the PDF as the number of samples increases. So we do 1500 or 15,000, and it looks more and more like a PDF. And we see that this looks very similar to what we got here using the command random variate, where we sample directly from the exponential distribution using Mathematica's function. And we can do the same thing for the Rayleigh distribution. So let's just say histogram, and then we can say we want 15,000 samples, and then automatic, and then PDF, and that will sample from the Rayleigh distribution and plot a histogram. And we can do the same thing here. So let's ask for 15,000 samples, and then do a histogram of this quantity X. And we see that, well, it doesn't look exactly the same. And that's, of course, the reason is I used the exponential distribution here instead of using the Rayleigh distribution. So now I discover a mistake when I plotted the results. So I should have copied this here, but I forgot to copy it. Okay, so let's do this again. And now we see that it looks like more like a Rayleigh distribution. And you can see that, let's try more samples. And more, and so on. Okay, so we can also try this here. Okay. Again, we can plot these histograms together with the PDF. and compare them. So I can say PDF and plot it in the same way that I plotted this earlier, and get a plot like this. Okay, so that concludes this video. Thank you for watching.